Our setting is about a global function field. So let X be a curve over FQ, which is smooth, projective, and geometrically connected. And we will consider a reductive group. The result will true for not split group, but for simplicity in this talk, we will only consider split reductive groups over FQ. Later, we will consider the sheaves when coefficient in QL for L not equal to P, and consider the dual group. So let's recall what are shtukas with and without level structure. Let I be a finite set. We have pre-stack of shtuka with I legs. So today in my talk, we always consider global shtukas, never consider local shtukas. So it's for any S scheme, Afan scheme over FQ. The S point of a stack of shtuka, so we notate shtuka indexed by E, the number of legs. S point. Classify I legs in X. G0 is a G bundle over X times S. So all the product are Q. With a modification between G0 and its inverse image by Frobenius. So this notation dou G0 means that we take inverse image by this Frobenius. Frobenius is on test scheme S. And this means that dotted point means an isomorphism out outside these legs. Where gamma xi are the graphs of xi. So this shtuka it is over xi. Legs are over xi. And now let's consider shtuka with level structure. So let N be a closed subscheme we have stack of shtukas with iPods and the level structure on N. Where we will note the shtuka IN indexed by I and by N. So in the definition, we will allow the legs outside the level. And the data we have also a trivialization of the G bundle over the level. Trivialization of G bundle with the trivial bundle. So this is a trivial G bundle over N. And we ask that this isomorphism is compatible with the level structure. Which means that if we call this right, should we make so this is the shtuka with level structure. The legs, they are outside the level, so it is over this. Now let's consider sheaves on these stacks. We have a morphism from a stack of shtuka with level to stack of shtuka without level, just by forget the level structure. And the stack of shtuka with iPods, they have a local model. They are the Bennigsen-Grunfeld Affan-Grassmannian with I legs. So it has a map over the Bennigsen-Grunfeld Affan-Grassmannian made quotient by some group. I will note it. Where this is the so it is over Xi, and this is a group scheme over Xi, which is a family version of a positive loop group, which acts on the Grassmannian, and we have a morphism which is formally smooth. The geometric zeta k equivalence give us power shifts on this Bennigsen-Grunfeld Affan-Grassmannian. Geometric zeta k equivalence. It says that we have a functor from the category of representation with coefficient in QL, finite dimensional representation of I copy of dual group. So this means I copy of the dual group. We have a functor to the category of power shift over Affan-Grassmannian with I legs, equivalent by this group, this family version of positive loop group.
Sorry, can you write the indices larger? Third generation index is half.
Oh, what are the index? So the index is the sum on infinite xi for all the xi the legs. Yes, this group will only appear here in this talk, but it will appear in Vincent Lafox's talk with the same notation. This it doesn't. It's not important for our talk. It's just a group scheme over xi, and which act on this. It's a positive loop group. We put it on this, and we already talked this in my course in May. And we have this functor which associated to each representation of I copy of G hat to a power sheaf on this equivalent by this group. We note it SWI, SIW. So this is a Sadake sheaf. So here are the sheaves. On this, we have the SWI. We defined a sheaf on shtuka without level. We call it FIW, which is just an inverse image of this sheaf. And we define sheaf on this. Just an inverse image by this map. In fact, this sheaf, it supports on a closed sub-scheme of this and the scheme of Grassmannian. So its support is grow EW. And this sheaf is support on some, so this is algebraic thing. So later we can only consider the shtuka where the support of this sheaf.
Did you say what row that one was?
It is support.
No.
Okay, I will say what it is. So it's when I is the singleton, and W is the representation associated to highest weight lambda, and we have the yo-yo affine Grassmannian with the weight lambda. This usually this notation, the Schubert closure of the Schubert cell. And this is just a global version of this kind of thing. So what I was saying, we have a shtuka without level structure. It is over xi. We have shtuka with level structure. It is over outside we have a map like this. So this is only over outside the level. We call this map alpha. So this is a GON tensor. It's a finite Itao Galois cover. finite Ito Galois cover of this, which is GON portion. ON is the structure sheaf of the scheme N. On this, we just defined the sheaf, this one, the pullback of the Sadaki sheaf. And now, today we will consider the direct image of this sheaf on the shtuka without level structure. So we consider a direct image of this sheaf. It carries on the structure level structure, and we will call this sheaf SL with the index I, N, and W. I will explain later why we call it SL. In my previous work, I considered direct image of this sheaf to X minus N copy I. So it's the same as direct image of this sheaf. And we proved that this sheaf is underneath over this. So I call this map B, the morphism of poles, the direct image of this sheaf. And today, we're interested in what happens on the level N. So I began state the theorem for the case I singleton for the simplicity. So now I take a point on the level. In the talk, I suppose it's of degree 1 for simplicity. So we take a geometric point over this. So we have so let's consider a shtuka with one leg. I is a singleton. X minus N. We have it will have the sheaf SL1. we will note eta, the generic point of X. And we let eta bar be a geometric point over the generic point. For any specialization map from eta bar to V bar. We have the setting, we have the nearby cycle functor for this sheaf. So this give us a sheaf on for on this we have we have a morphism from direct image of nearby cycle. To the nearby cycle of direct image. This is just the cohomology with compact support of the special fiber with value in this. And this is the cohomology with compact support of the generic fiber. Right. Sorry. And the theorem I want to talk today is that this functor is this morphism is an isomorphism. I will give some remark about this theorem. So this theorem is first proved by Anton for the UROK level structure, and then by Arnaud for level 1. Using iterated iterated nearby cycle and the whole lemma argument. then generalized for level 1, which means that n equal to v. Follow the same strategy. And today our proof, in fact, will also follow the same strategy with the general result about on the iterated nearby cycle. And for they go further than this kind of theorem. Then they did some explicit computation on the Lagrange parameters. But we will only stop on this theorem. We know that when P is a popomorphism, this functor is always an isomorphism. Unfortunately, in the case of shtuka, in most of the time, this map is not proper. So the theorem tells us that they still have the good property have by a popomorphism, even it is not proper. And when V is outside the level, we in fact recover the result that it is smooth. So we always have this diagram by the adjunction of the functors. So this is and when V is outside the level, the sheaf is well defined on V bar. We have this map, and here we have the specialization map. By geometric zeta k. The sheaf zeta k sheaf is euler to xi, universally locally acyclic for xi. So is over sheaf inverse image of this. So this is an isomorphism. So in this case, our theorem 1 implies that this is isomorphism. And last remark is related to Jean Lafogue's work on local Lagrange. So we always have global shtuka. In fact, we have a map from global shtuka to restricted shtuka, some kind of algebraic version of local shtuka. And the map is always smooth. Jean Lafogue, they considered a sheaf of this. Which is the product of Sadake sheaf when some sheaf comes from level structure. So this is the sheaf associated to regular representation of the GON. So this is you have point to quotient GON, and this sheaf is the direct image of this. If n is nv, the level is nv. And the inverse image of this sheaf is over SL. So the SL we defined before. This sheaf. And since the F is smooth, we have the near bicycle of our sheaf is the inverse image of the near bicycle of this sheaf. So our near bicycle is the same as the one they use in their paper. So this is about I singleton, and for general I. For general I, you have many ways to generalize the result. Here we only consider the most simple one. We consider the first leg on V and the other legs outside V, outside the level. So let I. So always we have an overshift on this. That's Li. That's N. So we consider FC only for the first leg. Here it means that we project our shtuka for the first leg. By the projection on, and we take a nearby cycle for this space. And this is enough for our further applications. So are there questions? Since no, yeah.
Do you have resulting higher nearby cycles?
Yes, if you want, you can put higher nearby cycles easy. I think the same proof works. Since for me, this is enough for applications, so I don't consider higher nearby cycle. But you will see as the proof works for higher nearby cycle. If there's no other questions in the rest of time, I will give a sketch of the proof. For the synchrotron case, the key ingredient of the proof and what is new comparing the case when V is outside the level. The new thing is the idea of Andrew Salomon, which relates to the nearby cycle of diagonal to the iterated nearby cycles. He used this result in a particular case, and we use a result which relate nearby cycle on the diagonal with the iterated nearby cycle in general case, proved by Edef Arnaud, Genestier, Laforgue, Gascory. So Vincent Laforgue will talk about this in his talk. So for the moment, it's a claim. So our strategy is to construct an inverse of the map phi. So and for this, we need a creation operator and annihilation operator. Idea is that we will use creation operator and then get nearby cycle on diagonal, and then we relate to iterated nearby cycles, and then we related it to nearby cycles over another diagonal and use annihilation operators. For this, let's recall creation operators. We have a morphism of stack over xi over x2. So I have shtuka with one leg on W. It is the same as shtuka with two legs, but the second leg associated to trivial representation. And this is a closed substack in shtuka with two legs. The second is we give it a bigger on a bigger stat, and this is by fusion. The shtuka with 3 legs restrict to a partial diagonal. So they are all over X2. This shtuka is over X3, and we restrict it for the first leg, restrict to X, and second and third leg on the diagonal. And what happened on sheaf? So the creation operator is the following comparison. So we began by a sheaf. And then this is we have a morphism of sheaf relates to a morphism of replantation. So this is induced by the trivial replantation to this one. The canonical map from trivial replantation to this one, induced by this. And this is by fusion isomorphic to a sheaf with 3 legs restrict to diagonal. So this sheaf is on this, restrict to this partial diagonal.
All away from the level.
Yes, outside level. I think yes. For the moment, we do not yet add nearby cycles. I think I like this. Similarly, we have a annulation operator. Okay. We have morphism of stacks over this for annulation. Okay. So this is associated to third leg. But this time restrict to the partial diagonal for first and second leg. Because we create a first and second leg, and the annulation operator is the composition of sheaves. So this time from sheaves on this. To shift on this, and then we go there by associated to evaluation map. So the evaluation map is associated to this. And now use this, we can construct our over the map in another thing. The reverse sense of map for the phi. So we began by this. And by the creation, we apply a near bicycle FC on creation map. But only for the second and third legs. And then we apply a direct image. So first apply near bicycle for second and third leg, direct image, and near bicycle for the fourth leg. Apply this to the creation operator, we get this map. Here, we use the claim to get this map. From this, to iterated a near bicycle. And then we have canonical map which send a PXC to XCP. So this is the canonical map. And then we have a proposition prove that this sheaf is constant sheaf over eta times I. So this is the isomorphic to XC on the diagonal.
I don't have the notation side 3, side 2.
This?
So the notation.
Yes. Okay. Compose with this.
This is okay. No. Next line. So there's
This.
yes.
So FC3 means the naive nearby cycle, which we send this to this by projection on the third leg. It's a nearby cycle in the sense most naive sense. So you have the shtuka with 3 legs. It is over this, and we can have a projection to this. And
which divider?
To this.
So you choose the divisor in base, right? It's like,
so the base is this. So then I consider the V on this, and here I have this. But sorry. Always by this projection. V. And this is the localization of this is a tri. So I use the base is just this. So everything is over this. The base is this one.
Okay.
And then I do this for the second legs. So this is the most naive definition of nearby cycle. We can also have the iterated nearby cycle, which is more complicated. It's over the generic point of these things. The base is more complicated. But the claim shows that all these nearby cycles are the same for the sheaf, the naive one or the iterated one. So I will just write down the claim. Oh, I didn't finish this. I will write down the alpha.
So this is
Yes. Yes. For the moment, it's a claim. So now I write down the claim for alpha. So let's first consider a case of shtuka with 2 legs. For some technical reason, the claim is not state totally at that one. We will also need we will also need the notation of switch the data. Which is the data, the diagonal switched by partial forbiddiness on X2. From XC. So this is the first step of the claim, where the XC2 is defined by project everything to the second copy of the curve. And XC1 is project everything to the first copy of the curve. And there are some compatibility results, such as the following diagram is commutative. So if we first do this, and we change. So this is because this shift is constant over eta times eta times eta. So this is commutative.
I have a question.
Yes.
Because I cannot read very well on the right.
Yeah.
Like you have the alpha, and you are taking here by side identity times the other 3.
Yes.
And then nearby cycles number 23.
Yes. Nearby cycles is on. So this nearby cycle is for the second. Is for this copy.
Yeah. Okay. But you have power, and you have the values by.
Oh yes. So this between this and this, there is a to move out this there to move out this power. There is a lamp. Easy lamp is just because of the partial forbiddiness action on XC. Such that for any n, once you take the direct image, they are the same. So it's just use the action of partial forbiddance on XC. When we take direct image, we can identify these things. And to get shtukas with 3 copies, I just finished the claimer and then I think I will stop there. So now we consider a shtukas with 3 legs. The following diagram is commutative. So this time, we will need delta n. I will first write down OTE. So SL, they always with 3 legs. So you can first do this for first do this for first and second, and then okay. So here, this means that so the idea is that you have one coordinate very forbidden compared with another coordinate. So the first one is very big comparing the second, and second very big comparing the third one. Oh, so here is given by alpha for this one and the third one. This is alpha for this one and this. So all these are given by alpha, but for different for not the same alpha. Alpha means kind of we put a diagonal with the iterated things. So this is their claim. So we use this to construct the map, and then to show that this is really the inverse, we have the very big diagram for adjectivity and surjectivity. What we need, except the claim, is just a proposition, and says that this, if we do FC, and then push forward, it is still a constant sheaf. So this is to give this map, this what I call beta. So this is constant, so you can switch here. And the proof of this is the same as in my previous work. We show that there are partial forbiddeness act on this this sheaf, and then we use Drinfield's lemma. And we can also show that there is an Ashler-Shimura relation on this. So then we use Drinfield's lemma. Now we will stop here.